Okay, hi everyone. This poster is about the dynamical study of emerging galaxy cluster using MUSE. This cluster is a redshift 0.6 SPT selected cluster, which has been studied on the X-ray using Chandra. On the left, we can see the pseudo-color image for the cluster with the X-ray emission shown in orange contours, exhibiting a typical distribution for mergers. We ask for 4 MUSE pointings, which are shown as magenta squares, positioned along the likely merger axis. From the MUSE pointings, we get around 80 cluster members, which we combine with previous Gemini data to study the dynamics. We're able to classify 2 main colliding structures, get velocity-derived masses, and then use a Monte Carlo analysis to get the likely time since collision. I also did some comparison with simulations and the study of the galaxy population, which I was not able to show in the poster. So please feel free to ask in Slack or join me in GatherTown at the poster B6. Thanks.
Hi, I'm Urmila Chadayammuri. I'm a postdoc at the Chandra X-ray Center in the Center for Astrophysics. And what I want to share with you is this method that I've developed to really constrain the history of emerging clusters using idealized simulations. This is enabled by a GPU accelerated code that I have, which runs 100 times faster than Flash, 10 times faster than Enzo. So we can really explore a large parameter space very quickly and efficiently. And so for the test case of Abell 2146, which is a bullet cluster analog, we're able to constrain the masses of both the halos, the impact parameter, the relative velocity, the dark matter, and the gas profiles, and the orientation of the system with respect to the plane of the sky to a very high degree. And we also managed to resolve a discrepancy in the literature between the mass measurements from the X-ray and SZ on one hand and lensing on the other. So if you have any similar merging clusters that you would like analyzed and weighed, please contact me. I'm at poster A11.
Yes, hello, I'm Malak and I'm a research and lecturer at Xiaoyuan Zhang University and Cavendish Laboratory at Cambridge, UK. In this poster, I'm presenting my latest model in studying galaxy cluster signals in different wave bands known as nodal model. Our technique moves away from this traditional approach of assuming specific parameterized functional forms for the variation of physical quantities such as pressure, density, temperature, and instead allows for a free-form grid construction for which the level of complexity is determined by the observational data in a fully Bayesian manner. I have illustrated our nodal approach in modeling the electron pressure profile in the analysis of a set observation of one of the max clusters in the clash sample using our very own telescope ASKAP-EMU in Cambridge. I am very keen on setting up a collaboration to continue improving our modeling of galaxy clusters and to obtain an unbiased estimate of the cluster masses among other properties. So please do let me know if you're interested, and thank you very much.
Hello, I'm Zhenlin, a second-year PhD student working in Astron and Leiden University. For this poster, I want to introduce my work on a shock detected near the viral radius of the Perseus Cluster. As we all know, the viral shocks play a very important role in heating most baryons into a hot and diffuse state. However, there is nearly no observational evidence till now. So previous ZwCl study on the Perseus Cluster has revealed a sharp temperature drop near the R200. In our work, with deeper ZwCl observations, we managed to confirm this shock both in temperature and density profiles. In our paper, we also discussed the origin of this shock, which is so far away from the cluster core. So more details about this work could be found in my poster D14. You are pretty welcome to see and discuss.
Hello, everyone. I'm Xiaoyuan from Leiden Observatory and Astron. Can you hear me now?
Yep.
Okay, yeah. So this is about 200 kiloseconds Chandra observation, and this cluster, the 1,000 X-rays of brightness edge was believed to be a shock that related to the southern relic, but our deep observation shows it is cold front, and the real shock front location is revealed by the radio spectral index map. You can go to D12 in GatherTown to talk with me, and also we have a cone-shaped subcluster in the north. So for further discussion, we'll continue on Slack and GatherTown.
Hi everyone, I'm Hyung Kim at Yonsei University. For 1 minute, I'm going to report our discovery of a very remarkable radio relic from the state-of-the-art radio survey called ASKAP-EMU. ASKAP-EMU is the precursor to SKA, which will increase the number of radio relics by a few orders of magnitude. Here we present the first discovery from it. A radio relic traces the location of the merger shock. The relic also we discovered is unique in many ways, but I will name only two. First, the shape of the radio relic is an inverted arc. Second, the radio relic is very close to the X-ray emission. For the inverted arc, we believe this might be due to the injection of cosmic rays from the neighboring galaxy. And the fact that the relic is very close to the X-ray emission implies that we just caught the very early stage of the young merger shock. For more information, please check my uploaded poster, and thank you for listening.
Hi, my name is Johan Zuñiga. Before reaching the dynamical relaxation given by virial equilibrium, galaxy clusters undergo thermodynamic state changes due to mergers and accretion of groups. We have proposed a method to quantify the degree of relaxation of this system from their observed global properties and based on the estimation of their entropies, considering some modifications in classical thermodynamic expressions to include self-gravitating systems and maintaining the accordance with the second law. Our methods were validated using both an information entropy analysis and estimation of the degree of relaxation of galaxy PDFs in the radial, azimuthal, and line of sight directions. We applied the model to a set of 70 well-sampled nearby clusters, obtaining good agreement between our results and previous observational measurements of the dynamical state of these systems. Thank you.
Hi, I'm Hyejeon, PK Research Fellow at Yonsei University. With my collaborators, James G. and Kyle Fiener, I'd like to present the first reclancing view of the emerging galaxy cluster A1240 shown on the left. Merging clusters act as natural particle colliders, thus we can use them as astrophysical laboratories to study dark matter cross-section, shock generation and propagation, and so on. One of our sample, A1240, hosts two extended diffuse radio signatures of the cluster scale merger shocks. In this cluster, the properties of X-ray emitting gas, radio relics, and member galaxies were examined in the previous studies. However, none have studied its dark matter yet. So we provide a weak Lenzing detection of its underlying dark matter distribution and total mass estimate. Also, combining with the other existing observables, we constrain its emerging stage. So please stop by A13 and check the details about these binary colliders with a 2-to-1 mass ratio. Thank you.
Hi everyone, I am Andrea Botteon, a postdoc researcher based at the Leiden Observatory in the Netherlands, and I am presenting a poster entitled The Initial Stages of Cluster Mergers Observed in Radio and X-rays. As many of you probably already know, when galaxy clusters are relaxed and are not interacting, we don't show the presence of giant synchrotron sources in the ICM. However, in merging system, we can see radio relics in the outskirts that are generated by shock fronts driven in the ICM during cluster-cluster collisions. And at later stages, we can observe central radio halos that are likely powered by the turbulence in the ICM. And recently, we started to study with LOFAR and other instruments whether it is possible to form radio diffuse sources even in the early phase of a merger, in the so-called pre-merger phase, so in the region highlighted by the orange box in the slide. As you can see, there is a big question mark on the right-hand side. So if you want to find out if this is possible, you are encouraged to check my poster and contact me via email or Slack if you have questions. Thank you.
Hello, I'm Jin-hyuk Kim at Yonsei University. This poster shows a new mass measurement of merging Hyejeon cluster algorithm based on recurrent analysis. Algorithm is very famous for a major merger and its extremely high mass, which might be tension with lambda CDM. So in order to test the rarity and to understand each merging scenario, accurate mass measurement is very important. However, the previous studies only reported the extrapolated mass because the observations did not extend out the virial radius as you see in the black box in the left figure. So in this work, we conduct new wide field HST observations that fully cover the virial radius as you see in the orange box in the second left figure. And we determine the mass without traditional mass concentration relations. Our updated mass is 23% lower than the previous weekly analysis, which is compatible with the weekly random CDM. If you want to know more details, visit our poster and read the paper uploaded to the archive. Thank you for listening.
Hello, I'm Andrea Botteon, and in the poster I will present an X-ray analysis of a low redshift massive binary merger. And the X-ray image is shown in the top image, and it shows a disturbed cluster. We looked for merger signatures, and we found the cold front ahead of the secondary in the northwest part. And also we found a plume of cool gas emerging from the primary and two possible shocks in the vicinity of the primary and the secondary. We compared our results with simulations shown in the bottom panels, and we found the merging scenario for the merging where the cluster is the secondary is close to the pericentric passage. Thank you.
Hi, hello everyone, greetings from Brazil. I'm Rogério Monteiro Oliveira. I'm a visiting professor at the State University of Santa Cruz, and I'd like to share with you some results of our team working on merging galaxy clusters. Our goal is to build a large sample of these systems, providing a detailed weak lensing mass distribution, plus dynamical analysis based on the galaxy's radial velocity, and when possible, provide a dedicated hydrodynamical simulations. We want to answer a very simple question: what happened in each case? I bring you two examples here. In the left, we have a merging cluster in which the main cluster presents a spiral-like structure in the X-ray distribution. And in the right, a bimodal mass cluster showing a single X-ray clump. So my time is running, and there are 4 papers in this poster. So I'd like to invite you to visit my poster. Bye-bye, thank you very much.
Sorry for that. I'm Ayşe Gültümer, a postdoc researcher. Can you hear me?
Yep, fine.
Okay, at the University of Utah. So when clusters of galaxies are formed, that's hardly the end of the story. They keep interacting with each other and with other large-scale structures and constantly evolve through violent mergers. You're looking at such a system of Abell 33, 95, and 91, which was recently observed by Rosita that shows an intercluster filament emission, as does Planck. XLM Newton showed a hotspot where 3395 meets the filament, and that's why we wanted to look at that region with NuSTAR due to its capability of constraining very high temperatures. But NuSTAR has a straight light issue, as seen in the middle panel, which we modeled, and our preliminary XMM and NuSTAR results do not show such high temperatures. We're currently working on a more precise description of the contamination of stray light, as well as the ICM properties. So please reach out to me if you're interested in the details.
Good morning, good afternoon, good evening. I am presenting a poster on Mustang 2. For those that aren't familiar with it, it's a camera on the Green Bank telescope. The big takeaway from that is the picture on the left. It's 100 meters in diameter, really big, and works up to 100 gigahertz. The camera itself, you've got over 200 detectors, and you combine that to get a 4.2 arc minute field of view, and then with 9 arc second resolution. And the important thing for this conference is if you've got a high redshift cluster, it's ideal for observing them. Get down to Compton Y's of 2 × 10⁻⁵ in just an hour, or you can go deeper, reach sensitivities of 10 microkelvin per beam. Some of the stuff, the science we've done, very varied. You can look past point sources and see your favorite cluster, or you can do surveys of clusters that you haven't got much resolution on from other experiments and find out their profiles. So if you want to use it, it's there. Come speak to us. And thank you very much.
Okay, hi. Using numerical simulation with GCF2021 code, we found a model for the collision of Abell 2034. In this cluster, the gas lies between the two dark matter peaks. From the numerical model to better represent this collision, we carry out 9 simulations varying the concentration for gas and dark matter. Of this exploration, the figure on left in the upper frame shows all collision models obtained from different gas concentrations. The contour curves represent the dark matter distribution, and the colors represent density, temperature, and X-ray Mach. Likewise, the lower left figure shows different models with different dark matter concentrations. It is possible to notice different dissociation levels. Finally, from offset analysis in the right frame, we conclude that models with different gas concentrations are more important for these displacement levels. Then, for more details, look at my poster on C9. Thank you so much.
Hydrodynamical simulations of galaxy cluster outskirts revealed 2 key features that have serious evolutionary implications, as they both work to create a non-homogeneous intracluster medium: accretion shocks that heat gas as a result of infalling material and density enhancements. By studying the changes in H1 absorption characteristics as a function of radius, one can determine the location of the accretion shocks and directly probe the interface between the outskirts of the galaxy cluster and the intergalactic medium. As opposed to X-ray or SCE studies, I'm looking at very, very diffuse cluster environments in the far outskirts of clusters. The only way that we can directly detect the gas is via UV quasar absorption line spectroscopy. This provides extremely sensitive line of sight observations in which we expect to detect a suppression of H1 due to the accretion shocks. A key question we aim to answer is how far this suppression extends, since virtually no such observational constraints currently exist for models of cluster formation and multi-phase gas physics of ICM outskirts. If you'd like to learn more, please visit my poster.
Hi, I'm Jack Goucher. I'm a graduate student at the University of Pennsylvania. In our recent paper, we measured the MADCAS mass richness scaling relation as measured using the SC inferred masses from the most recent ACT data release, DR5, which came out in the past year. We found a high slope for the mass richness scaling relation of about 1.84, which we attribute to line of sight non-virialized contaminants in the MADCAS richness relation. We also found an intrinsic scatter in the mass richness scaling relation, which is consistent with other measurements. We also investigated the radio and IR properties of the MADCAS clusters as well as the ACT clusters, and we made estimates of the amount of SC infill of the SC signals due to radio and IR contamination. And feel free to Slack me or visit my poster if you want to learn more.